Have you ever wondered why voltage drops occur in transmission lines and what factors make them worse? Today, we're diving deep into one of the most fundamental concepts in power systems, voltage drop in transmission lines. In this video, we'll explore how resistive and reactive components affect voltage drop, understand the impact of power factor on line losses, and discover why reactance plays a dominant role in power transmission. We'll use Phasor diagrams to make this complex topic crystal clear. Whether you're an electrical engineering student preparing for exams or a professional looking to refresh your fundamentals, this video is for you. So let's get started and unlock the secrets of transmission line voltage drop. This is the receiving end voltage VR. This is the load current I. So this is the resistive drop IR, and that will be directed along this load current. This is the reactive voltage drop, say J into capital X into I. Say this angle is phi. That means the angle between the receiving end voltage and load current means the angle load voltage load current is phi. So power factor of the system is cosine phi. Say this is sending end voltage Vs. Now we will extend this line means along the direction of VR. Now what is this angle? Obviously this angle will also be phi. Now what is this? This is the cos component of IR, means the component of the voltage drop IR along the voltage VR, and obviously that will be IR cos phi. So this angle is also phi. Now if we draw a straight line parallel to the direction of VR, then this angle is 90 degrees minus phi. So the component of Ix along the direction of VR will be Ix cos 90 degrees minus phi equals to Ix sin phi. So from this figure, the total length means VR plus IR cos phi plus Ix sin phi is the length of the straight line from this 0 point to that point. Say this is A and say this point is B. Now the angle AOB is very small, tending to 0. Very small compared to angle phi. So we can write Vs, sending end voltage, is nearly equal to this voltage, means VR plus IR cos phi plus Ix sin phi. So Vs minus VR equals to IR cos phi plus Ix sin phi. That is the difference between sending end and receiving end. That means the line drop. Obviously, this line voltage drop increases when that current I increases. The voltage drop also increases if R increases. The voltage drop also increases if X increases. So we have seen that the voltage drop in transmission line increases when the load current and resistance of the line and reactance both increase. Now when phi increases, cosine phi decreases. If cos phi decreases, then if R and I are fixed, then Ri cos phi decreases. So resistive drop component along the receiving end voltage decreases with increasing phi, means with decreasing power factor, because cosine phi is the power factor. At the same time, Xi sin phi increases, because when phi increases, sin phi also increases. That means the voltage drop due to Xi sin phi will increase. Now in power systems or in all transmission lines, the reactance value is much more than the resistance value. So the influence of decreasing Ri cos phi is much less than the influence of increasing Xi sin phi. So overall, voltage drop across the line will increase with increasing phi. So the voltage drop increases when phi increases as phi approaches 90 degrees. And that's how voltage drop in transmission lines works. Remember, poor power factor means higher voltage drop because reactance dominates in power systems. If this helped clarify the concept, like, share, and subscribe for more electrical engineering content made simple. Drop your questions in the comments below. I'd love to hear from you. Thanks for watching and see you in the next video.